Dear students, now we are going to discuss full subtractor and its logic diagram in detail. Full subtractor is a combinational circuit that performs the subtraction between three bits. Simply, full subtractor means subtraction among three bits. The three input bits are minuend, subtrahend and borrow from the previous stage. There are two output bits, a difference and a borrow. This is the general diagram of full subtractor where A, B and B in are the inputs. Here this A is the minuend, B is the subtrahend and B in is nothing but the borrow from the previous stage. B out represents the output borrow bit. So here the basic rules for binary subtractions are 0 minus 0 is equal to 0. The difference is 0, there is no borrow. Next 0 minus 1. Here the minuend is smaller than the subtrahend. In that case we have to borrow one bit. So here we have borrowed 1. So here borrow becomes 1 and 1 0 minus 1 is 1. So difference also 1, borrow is also 1. So next one minus 0 is equal to 1. The difference is 1. There is no borrow involved. 1 minus 1 is equal to 0. So here the truth table for the full subtractor. Truth table relates the input and output combinations. For 3 inputs, there are 8 combinations from 0 to 7. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Let's see each one. So here 0 minus 0, 0. Then 0 minus 0 is 0, 0. Here we have to perform subtraction for this to first. Okay, 0 minus 0, 0. The result is 0 here. So 0 minus 1. So here the second rule. Okay, so here minuend is smaller than the subtrahend. So at that case we can get difference is 1, borrow is 1. Okay, so this is the second case. The next one 0 minus 1. Again the second rule, right? So 0 minus 1 means here the borrow is 1. Then here we are getting the difference. The answer is 1. Borrow is 1 and the answer is 1. So that 1 minus 0 is 1 again. Okay. 0 minus 1 means what? Borrow 1 and difference 1. That borrow we can write it here and the difference is 1. That 1 minus 0 is 1. So next 0 minus 1. Again 0 minus 1. The second case again. So here the difference is 1 and the borrow is 1. That borrow is written here. Okay. Then the difference is 1. The difference 1 minus 1. Correct. The result of this subtraction is 1. That 1 minus 1 is 0. Do you all understand this? Okay. So next 1 minus 0 is 1. So here the result is 1. The difference value is 1. So 1 minus 0 again 1. There is no borrow. So next 1 minus 0. So here the difference is 1. There is no borrow generated. So this 1 minus 1 is 0. So here 1 minus 1 is 0. 0 minus 0 is 0. The next case 1 minus 1 is 0. Then 0 minus 1. 1 minus 1 is 0. 0 minus 1. That is the second rule. Here borrow 1, difference 1. So this is the truth table for full subtractor. Okay. So for this difference values and output borrow values, we are going to obtain Boolean expressions. For that we are going to use K-map method. K-map simplification for difference. Here, 3 bits are used in full subtractor. So, this is the K-map format. So, A, B, B, A. 0 represents A bar, 1 represents A. Likewise here 0, 0, 0, 1, 1, 1, 1, 0. So here we have to write down the values of difference with respect to this truth table. 0, 0, 0 is 0, difference value is 0. For 0, 0, 1 its value is 1. For 0, 1, 0 its value is 1 like that. So here we can have the difference values for each combinations. 0, 0, 0 its value is 0. 0, 0, 1 its value is 1. For 0, 1, 1 its value is 0. For 0, 1, 0 its value is 1. So we have to fill it up all the values. So now we are going to consider only the higher bit here. In order to obtain the Boolean expression, we are going to consider the higher bit. So we can write the difference is equal to this combination A bar, B bar, B in plus for this one we can write A bar, B, B in bar plus for this one the value is A, B bar, B in bar plus for this one its value is A, B, B in. Okay. So after writing this expression we are going to simplify it further. So for that we have to take the B in. So which all are the common terms? Here B in is there, likewise B in here. So take B in, that is input borrow value as a common one from this two expression. So we can write B in of A bar B bar plus AB plus from these two expressions, okay, values, B in bar is a common one. So we can take it outside. So B in bar of A bar B plus AB bar. So next, this is nothing but A bar B bar plus AB bar is nothing but the complement of the XOR operation. So we can write this expression as complement of XOR operation of A and B. So B in into A XOR with B, the complement, plus B in bar. So A bar B plus A B bar is nothing but the XOR operation of A and B. So we can write this combination as A XOR with B. So here for further simplification, consider this A XOR with B is represented as capital X. Then its complement is denoted as X bar. So we can write this expression as B in X bar plus B in bar into X. It looks like the XOR operation between B in and X, right? Because B in X bar plus B in bar X. So it is nothing but the XOR operation of B in and X. So we can rewrite this expression as B in XOR with X. In the next step, we can replace this X with the given value A XOR with B. So here it is XOR, okay. So here we can replace this X with A XOR with B XOR with B in. So this is the difference Boolean expression. Okay. So this is the Boolean expression for the difference A XOR with B XOR with B in. Similarly, we can obtain the K-map simplification for borrow. So this is the K-map representation of borrow. Okay, so here we can obtain borrow for the combination of 0, 0, 1, 0, 1, 1, 0, 1, 0 and 1, 1, 1. Then we have to obtain the borrow expression like this. So here we have to group the ones. So even number of ones can be grouped together. Okay, so even number of ones here. So here the common term is A bar. For this two, okay, that orange color. For this two ones, the common term is A bar and the remaining common term. For this, it is B in. So we can write B out is equal to A bar B in plus the next one is we can group the next two bits. Okay. For these 2 bits, the common term is a bar and here the common term. For this 2, this b is a common. So we can write a bar b plus and the last group. So in this one, the common terms are b, b. So we can write as such. So this is the Boolean expression for the borrow of full subtractor. Next, we are going to draw the logic diagram for the full subtractor. We have already obtained the Boolean expressions for the outputs, difference and borrow. So for these expressions, we are going to draw the logic diagram. The difference is equal to A XOR with B XOR with B in. So here we are going to use a single XOR gate with 3 inputs. So here this is the logic diagram for full subtractor. In order to get the difference, we need to use one XOR gate. So this is the XOR gate with 3 inputs. So inputs are A, B, B in. We can obtain the difference of the full subtractor. After that, we are going to draw the AND gates for this borrow. So borrow here A bar B plus A bar B in plus B, B bar. So here we are having A bar, that is the complement of A. For that we need to get one NOT gate and there are 3 AND gates to multiply these values. Finally, we need to have one OR gate. Okay. So here that A bar can be obtained by using one NOT gate. Okay. So we can obtain A bar B here. So this is A bar. This A bar and B is given to one AND gate. And this B, B in is given to, both are given to one AND gate. Likewise, A bar, B in are given to one AND gate. So 3 AND gates are used here. So the outputs of AND gates are given as input to this OR gate to get the borrow value. Okay. So here we are going to use one XOR gate, 3 AND gates, one NOT gate and one OR gate. So in order to realize the full subtractor, we need to have one XOR, one NOT, 3 and one OR gates. Okay. Applications of full subtractor. Full subtractors are used as a basic building blocks in arithmetic and numeric computations. It is used in the design of digital calculators. In processors, it is also used in arithmetic and logic unit circuits. So these are the applications of full subtractor.